Welcome to Computability Freaks. I'm your host, Erin Carmody, star of the hit television show Computability Freaks. Won't you come with me on this journey through Soare, the Art of Turing Computability, Theory and Applications. Today's episode is the Parameter Theorem. Welcome, freaks. And so I'll start with so I'll start with the story. Imagine we're watching a movie, okay, and it's like we see so far that it's a couple, and it's not a couple. There's just two people that you can see that they've known each other before. They knew each other when they were younger, and they're at a bar, and so they're like reconnecting or something. We don't really know what's going on, but it seems like everything seems really normal. But then the guy says to the girl, that are talking, he's like, so what's your name? And she says, oh, wouldn't you like to know? And then we realize there's something different going on there. We don't know their names. I don't know their names. They don't know each other's names. Why wouldn't they know each other's names? Okay, so the idea is that in this world, if the girl tells the guy her name, then he knows everything about her. And he knows everything, her thoughts, everything that brought her to this point, and where she's going and where she's been. He knows everything. Okay, so they can't reveal their names, and this is like girdle coding. Okay, so this is so important. And today we're gonna talk about the parameter theorem, but we'll like go back to we'll at least mention those other two theorems or two or more theorems that we did from last time. Okay. Okay. So let's just talk about like the girdle coding for a second. And I hated I watched the video back last time and was like, I said the girdle coding, you do this, and it just like the example was so bad because I didn't even look at it. I wasn't thinking. Okay, so but let's just think about how amazing this is, this girdle coding. So because we really need it today. So we have a function x plus 1. It's a computable function. The domain is 0, 1, the natural numbers. The codomain is the outputs are 1, 2, 3, and so on. But you think about this is actually, even if you have girdle coding, that's a lot to code. That's that's infinite string of numbers. How are you going to do that in the finite number? Okay, well, it's finite, so we don't do that. We go and we write it as a Turing program. In this case, this Turing program is really simple. You don't have to do anything because if the input is 2, then on the tape will be 3 ones, and so you just don't do anything. You just immediately go into the halt state and stop. Okay, this is something finite that we can code, and so that's what we're doing with the girdle coding. And let me just write this again. It's okay. I do get. So let me just write some set. The set I know what happened. The set I wrote was very similar to the primes, and so I changed the set, but I didn't go back and fix it. Okay, so let's just say we have a set. Let's just do something weird. 3, 5, 29, and 11. Then we could code this as prime 2 to the 3, 3 to the 5, 5 to the 29. So this code, then not only you have this codes the set, but you could because of unique prime factorization, you could decode it and grab the set elements. Okay, and that's what we need to. So not only for us, our program P sub E computes phi sub E, this computable function. This is the program, and this is the function, the partial function. Okay, and so but this E is the index. But it's not just a number. I was like, oh, who cares what number you are on the list of Turing functions? Well, it's actually your source code. So this index E, you can unravel it and it gives you the whole program. Okay, we needed, and we did use that for the universal machine theorem. So I'm gonna go ahead and just state the parameter theorem right now. Okay, we'll talk about it. I mean, whenever you say the word parameter, my brain just goes, I'll just think about that later. Let's talk about something else. Okay, parameter theorem. Okay, so I'll just state it as it's stated in Soare, and we'll talk about it. Okay, so there is a one-to-one computable function SXY such that for all X, Y, Z, phi sub SXY on input Z. So the program coded by SXY on input Z gives the same output as program X on input YZ, thinking of Y as a parameter. Okay, and I'm going to spend most of the time just kind of talking about how what this means, how we can think of it, and what's a parameter and stuff like that. Okay, let me just go over here for a second. So I just want to make sure that I got that totally right. Okay, there is a one-to-one computable function SXY such that for all X, Y, and Z, this is true. Okay, so we just have to unpack what does this mean, and also we'll go through the proof. Okay. It's like you want to like burst everything out at once. Okay, but we have to do that. Okay, so first let's just talk about like a parameter. When I hear the word parameter again, it's like, why'd you have to say that word? Okay, so it's like a variable, right? But let me just think of, I'm thinking of some specific examples just to get an idea going. One thing would be, I'm going to take this down here. One thing would be the normal distribution. Okay. Okay, because I'm teaching stats. So, okay, well, this is the normal distribution. And we think of it, so I think of, when I think of parameters, there's some kind of meaning going on. Because introducing a parameter, there's something, okay, to me, it's like you're introducing some kind of meaning. You're saying we're thinking of this variable as a parameter or whatnot. Okay, so this is, we could think of this as, it's the parameters here are sigma, the standard deviation, and mu, the mean of this normal distribution. And depending on the parameters, this might change. So like a mean mu, a mean of 0, and a standard deviation of 1, they all look the same, right? But then you could adjust the parameter so you have a mean of 1, maybe standard deviation of, I didn't draw that great. Or maybe you want to do a mean of 0, but you want to make the standard deviation bigger. So maybe something like this, more spread out or something. Okay, so we have all these, the normal distribution, we think of the mean and standard deviation as a parameter, because we don't really, otherwise you could think of this function as like a function takes in three inputs and 1 output, so like this 4-dimensional function, but that's not really like what we mean by it, right? We just mean we're trying to classify all these functions into one equation using these parameters to say different outputs. Okay, so I'm imagining, sorry, should I go there? Or maybe I'll mention another type of thing you might think of, like a parameter. Okay, so suppose I have this family of functions, x squared over 2 plus c. They did this, like this family of antiderivatives of the function, just y equals x, or f of x equals x, little f of x equals x. And so again, we could think of this as a function of 2 variables. Actually, we have a picture of it here. Okay, you could think of this as a function of 2 variables. I didn't even like talk about the parameter level, what that means right there. We did mention what it means, but we're going to talk about it more. Okay, so I have this thing, this thing, I mean, it's a thing. If I x squared over 2 plus c, I wrote it here as x squared over 2 plus y. But really, we're interested in, we're talking about this, we're this family of antiderivatives. We're interested in like the family of curves it makes as you let c vary. So here we could say, c is, I'll just, drawing skills there. Okay, just like this. And so we have this, and so it varies as c varies. So this is a c as a parameter. Okay. Okay, so imagine what am I trying to imagine right now? Are we going back to the thing, or okay, yeah, so let's go back to the thing. So imagine I'm like this head. So I'm this like, I am this program, and I mean I'm this yeah, I'm a computable function. Okay, so here's me. I'm like the mother, the head of this whole operation. Okay, and what can I do? I'm the I can compute the normal distribution. So I can compute let's bring this thing down. So it does not have to be about the normal distribution. But okay, so I bring this thing down. So I can compute this thing. Okay, but but you know, I think of it as like, I'm going to think of the standard deviation as a parameter. So we could have more than one, but this is a parameter. Or it's just easier for me to think of the mean as a parameter. Okay, you can think of both of the parameter. I hope the analogy is not just being being lost. Okay, so I'm this thing, and I can compute this normal distribution based on these variables. Really, you know, mu, x, and sigma are the variables. But I'm going to think of it as, you know, I think of my little children, and they all can compute their you know, this is like mu equals 0, mu equals 1, mu equals 2, and I think of them all as they compute this slices. So we're thinking of these slices of this function according to different means. Okay, so like this guy over here, he has mean 0, so he calculates all of these, all the different means with different standard deviations. Sorry, that doesn't look good. Okay, and this guy calculates all the means that are, here's 0, here's 1, and so he has all these graphs. He makes all these graphs. Okay, so this theorem is saying that okay, I go to one of my children now. They have to. So I go to one of my children here. They have their own program. I have my own program here, and this theorem says that that I can find the index of my program, aka I can actually find my program. Okay, find it with the index of, let's say this index E of the mother, and which slice you are. With that information alone, this program, that's a lot of information though, because you have my whole source code. But with this information, you can create your own program. Okay. Let's just go back to the statement again, just to make sure we just have it in, and we're going to talk about it again. But okay, so this is. I had some. Let me look up here for some. I had some interesting way to think about it. Okay. Okay, just stick with me here. That one is not bad. We could do that. Okay. Okay. The one thing I was thinking about was, okay, let's just do this one. Okay, let's think of this. Okay, okay, let me, I'll just write it again. Okay, so suppose, just think about this, and then we think of the maybe the normal distribution. We can think about that, but we can also think of this function. We did z, y, let's just do x, y. xy equals x plus y. Okay, so let me see. So remember that. Remember how we did that code is really, it's pretty easy, right? Like this one was, you didn't have to do anything. You just, you're in the start state and you're reading a 1 and you go to the right and you just you basically go into the halting state and write a 1 and go to the right. You might have to erase 2 numbers or something, but it's pretty easy because you have it's set up. It's a multivariable function, so it's set up. You're adding 2 numbers, and so you have 2 inputs. So it's nicely set up. So this program wasn't that hard. So that's what I'm thinking. But now if we think about when we did that homework, and we're trying to think of all these other functions, thinking of y as a parameter, we have like f of x equals x plus 1. We have f of x equals x plus 2. And we have f of x, or let's say f prime maybe, f double prime of x equals x plus 3, etc. These programs were harder to write. They were definitely harder to write than this one, than the one with 2 inputs, because it's this thing is adding 2 numbers. It's sort of built to be it's most convenient when it's something where you're given 2 inputs to find the sum of 2 things. But these programs are actually, so this is actually easy. These are actually harder. I'm trying to think of like what this theorem means. These are actually harder programs. Especially like the x plus 3 one, we had to add 1. We had to get to the end, and then we had to add 1 and then add another 1, or add 1 and then add and then get the halting state to add 1. Okay, but it was definitely it was difficult to do 2x too, and add x plus x. Okay, so anyway, these are harder to do, but it's saying that the parameter theorem says that to find a program for, let's say, f of x, you can use the code, let's call this the mother, for e plus which slice. In other words, which y equals, let's say, 3 or whatever. Okay. Okay, so within this information, you can get the index for your program, and therefore if you have the index for your program, you also have the code for it as well. Okay, so let's do okay, and also, so another thing, just thinking about this theorem, let's state it again, and then we'll do the proof. Okay, so let's see. We get some other little fun reading things later. Okay, so let's say the parameter theorem. There is, so the star of the show is this SXY, 1-to-1 computable, such that for any x, y, z, phi s, the program SXY on input z gives the same output as program x on input yz, thinking of y as a parameter. Okay, I think of it like this mother, it's set up. I'm a multivariable function, and so I should be set up with multiple inputs, and I can calculate accordingly. These children of mine are a slice, and their program is a little awkward because it's harder, because it's really, you're adding 2 things together, so it'd be nicer to just have 2 inputs to add those things together. It'd be a lot easier, but they can refer to the source, the E code, and which slice they're on to find the code. Okay, so what I was going to say is, of course, these functions are computable, right? These are all computable. So this is computable. So any slice is going to be computable. But, and so it does have a program that computes it, and so it does have a code from like Girl coding, or whatever your coding system is. However, that it's like, but how is it connected to the mother? And so this is like, it's connected because you use that code, you the input for S. So the input of this thing here, the name of this program, all it needs is the input is the X, that's the code of the mother. And then Y is like which slice. Okay, this might be convenient. Okay, so I think with parameters, it's like if you're talking about parameters or something like that, there's some meaning like tied to it. You know, we're thinking of normal distribution with these parameters. We're thinking of the family of antiderivatives as a parameter C or something. Okay, so it's like what you mean. So I guess it's like I'm when I say I'm this guy over here. I am okay, so what I was gonna say, so that's computable. Okay, okay, I have my code. Oh, I'm a multivariable function. That's that's where my natural state. But this is saying that you can think of yourself, if you're a multivariable function, you can think of yourself in slices. Okay, we'll also talk about the one-dimensional version later, I think. But you can think of that. It's a little bit harder to do. Maybe in programming, this is you actually have to do this, but it seems a little harder to do. Okay, I'm actually a multivariable function, but I'm going to think of myself actually as a function of one variable with a parameter, okay, or something like okay. And so that program might be harder because I'm naturally a multivariable function, but this is saying actually we can find it just from your code and which slice you're interested in. Okay, so let's go through this proof. I feel like there's like I feel like there's a lot of things to say, but okay. Okay, so let's just go through the proof of this parameter theorem. Okay, so we have phi s x y on input z has the same output as p sub x y z. Thinking of y as a parameter. Okay. Okay, so there's this algorithm. Program PSXY on input Z. It has X. It knows X is an input. So it inverts code X to get program P sub X. And then apply P sub X to input YZ, where your Y is like, you defined it to be something. So it's like, oh, I don't, okay, my program is, my child's program is Y plus 3. It's like, what do I do? So I'm going to go back to, I know what X is. I know my mom's name. So I'm going to go back, uncode it, go figure out that program, and then plug in 3 and Z. And then I get my program. Okay, I'm thinking of that documentary of Mother. I can't remember what it's called, that documentary, but it's like a cult where there's like the mother. And so I guess it's kind of sad, but it's just that's kind of what I was thinking about it. Okay, so the algorithm, okay, then we apply px. Okay, this procedure defines an algorithm with inputs x and y. Okay. Okay, this is an algorithm. So by TT, it has a Turing machine index. Okay, so this is like a computable algorithm. There's a Turing machine which computes it, and it has the same index. this algorithm has index SXY. Okay, it says it's easy to check that SXY is already one-to-one. Okay, so I think about this. Okay, so I've got this situation here. I'm a multivariable function. I've got my slices. Okay, my name is E. This slice here is, we'll just do triangle, slice triangle. And over here I've got this other program F, and it's got all its slices. It's a multivariable function, and it's got its slice star that we're interested in. So somehow E triangle is not equal to F star. But say somehow this situation happened that S of E triangle is equal to S of F star. Okay, these are totally different things. And it could just be, what if they're just two different slices of the same mother? What if they're just two of these slices? Could they somehow have the same like index, therefore like code for their program? So these two things would somehow, well, this maybe, these two things, they somehow have the same program. Like that shouldn't, they're computing the same thing. Okay, but let's say that did happen for some reason. Okay, let's say that did happen. Let's say that did happen. Then replace S X Y by an obviously by, let's say, by S prime XY by an obviously one-to-one computable function. Okay, so that phi S prime XY equals phi S XY by using the padding lemma. Okay, the padding lemma says that any program P sub E has infinitely many indexes. It's, and that this like list of indexes is computable. The characteristic function is computable. Okay, so let me just, okay, so we're going to replace it by something that is obviously one-to-one. So if we're worried about these programs being the same, let's just pad one of them. So we're gonna pad like, let's just pad this one. So it's, so that these are not equal. But but by the padding lemma, we could change these so they're different. So you might say, okay, well, how are we going to make sure that that doesn't like mess something up later? So he's going to be defining S prime xy in increasing order of xy, where xy is the image of xy under the standard pairing function. Okay, so we have this, our E triangle is not equal to our F star. Okay, and so you're like, well, how do I, somehow they ended up with the same program. So how do I decide which one to pad? Okay, so I'm going to say, okay, E, by the pairing function, E, these are natural numbers. E triangle somewhere on here, and let's say F is maybe up here. Then we'll pad this one. If you put these two into the standard pairing function, you get a natural number. Compare those two and pad this one. Okay, and any other two that then, okay, maybe that one now that makes it the same program as something else or something. Then, but those two inputs are different somehow, so they're different. They have their image under the pairing function is different. So you can pad one of them. Okay, that's what I think is going on here. Okay, so I just want to see. So he says now it says then this is called, it's also called the SMN theorem. I'll stick with parameter theorem just in case. Okay, so he says the okay, let's go back to the parameter theorem here. The statement of theorem here. Okay. So he's saying, so this the parameter theorem is also stated for an M tuple. So this thing here, you can think of, it could be an M tuple. And this could be an N tuple, this Z. And then the function S is S N M X Y. Which gives the theorem its name. And here M and N is 1. But he says, but by the pairing function, we can identify this M tuple with a single Y. And likewise, code these into 1Z. And then he says, we achieve notational convenience without loss of generality. Awesome. Okay. Okay. Okay, so there's a whole lot of meaning in there. And that's the only theorem we're going to do. Okay, the other theorem for this section is the unbounded search theorem. So but let's just, since we're like getting good at this, let's rewrite our theorems and then we'll look at some other stuff. Okay, so let's rewrite our theorems. So the first one is the padding lemma. For any program P sub E, I should say any program P sub E has infinitely many names. And this list of names is computable. And the instructions will essentially be the same. It's just some of them might have some extra instructions that we don't need. Okay, the other theorem is the enumeration theorem, and I just like to call it universal machine. universal machine says there is computable it's a partial computable function. Sometimes I don't like that it's a partial computable because it sounds like it's partially computable instead of it's just that it's partial function. Okay, a partial computable function phi e x, which takes as an input Turing program E and calculates h. So we can just write that now. That means that it's calculating Turing program. It's the word calculating. And that's I always get. So it's this computable function, partial function, takes input a Turing machine index, and the input for that, and an input, and it calculates the output of Turing machine E on input X. Okay, and then there's something else to it too. Say by TT, there is some I a code for a program such that the program takes as input EX, takes the Turing machine E as input and X as input, and it gives output that program E would give on input X. Okay, and then we have the parameter theorem. And so the Gödel coding has been really heavy Gödel coding. The parameter theorem says there is SXY one-to-one computable function such that for all X, Y, Z, the program SXY on input Z gives the input of program X on input Z, thinking of Y as a parameter. And okay, say my name. So yesterday I was getting ready for this, and I was watching The Never Ending Story. So The Never Ending Story is about a kid that hates math, has so much math anxiety that he skips math class, and then he ends up learning about the empty set and unbounded spaces. But I keep thinking, why does he have to say her name at the end? Like, he has to say her name at the end. And I guess it's Moonchild is what he says. And the story, it's talking about all about like creativity and imagination and stuff. But I found this online. This was funny. So it seems silly that a new name might save. So like he saves the whole spoiler. This like 40-year-old movie. No, I don't know how old it is. It's like the 80s or something. Oh wait, I'm 40. Oh wait, I'm older than that. Never mind. So so anyway, so it's like, but he has to like save this whole land by saying her name, coming up with a name and saying it. And so maybe it's like about creativity. But we see with these Gödel codes, the name is everything. The name of the program is the program. Okay, so I just read this. It's if it seems silly that a new name, this is from Looper, it might save someone's life, then you haven't considered the power of what we call things or the power in words themselves. Bastian, that's the little boy, is called terrible names by the school bullies, and this certainly affects how he feels and sees himself. With the arrival of the nothing, the childlike empress also loses an aspect of herself that must be reinvented. And one way to accomplish this is by adopting a new moniker. Padding lemma, anyone? This new name would be a new start for not just the empress, but for a whole new world. Not to mention the name Bastian chooses for the empress, Moonchild, perfectly suits her as being a beautiful tribute to his dead mother. Okay, and I think about the mother program and the slices, and then they call out and they say, and then or maybe they say to the mother, say my name or something. Or I was thinking, yeah, maybe she says that to them, say my name, so that they can, once they know her name and what slice they're on, then they can figure out their own name. Okay, what else? Another thing, okay, well, we'll just here, I'll look at these comics. I was really into Ellis Rosen lately. Just everything's just hitting the right spot. This one, at least this supports my theory that we live in a computer simulation. Okay, maybe we could, I don't talk about that sometime. I do think we live in a computer simulation. I think that's the only way that we'll be able to forgive God or something. No, sorry. So no, I do think we live in a computer simulation. I hope we do. That's funny. And then I like this one a lot. This one was really funny. Okay, I was thinking we were going to talk about this like recursion theorem, the Claney recursion theorem. That's also, by the way, Claney is the person that did this, and we're gonna, I believe that's how you pronounce it. We're gonna look at that paper in a second. But there's a recursion theorem. It's sort of like a one-dimensional version of this, but I feel like maybe I'll do that next time. Okay, but let's read this comic. I just love this. Bob Henderson. I'd recognize that face from my extensive database anywhere. I don't know why, you can just hear her voice. It's so funny, but it also reminds me of the Jetsons robot lady. Okay. I thought this was funny because it kind of sort of had to do with our like input output thing. And also about the creative process, because we were talking about that a little bit last time. Okay, this is Ellis Rosen, I believe. Okay, how would you describe your creative process? I think it's all about input and output. You can't have one without the other. I have to read, learn, socialize, do chores, and just generally participate in the world. I agree with that. If you don't do anything, it's kind of, you don't have a lot of source material, you don't have a lot of material. That's the input. All of that builds in my mind and comes out when I sit down to sketch. Sleeping is important too. I've gone to bed without any ideas and woken up with a bunch of popped in my head. I sometimes think my subconscious is smarter than me. Yeah, I hear that. Okay, I also go back to old sketchbooks often. An old half-thought idea that didn't go anywhere can suddenly have new life when you look at it a year or even just a month later. Geez, that's true. I like looking at old notebooks and stuff. Yeah, but I'm not Ellis Rosen, but it's like I like looking at I like looking at old notebooks and stuff. And it's like, where'd you get that stuff from, lady? Okay, so I wanted to look at a couple things. Okay, I guess maybe we will just like look at this. I saw this because I was like very confused for a while. This was online, a blog. I put it in Notability, so it looks like this, but it was interesting because it was a student of Joanna Franklin. So that's Professor Joanna Franklin, yeah, in New York. Yeah, she's a great computability theorist. I actually just saw her at JMM giving a really good talk. Okay, so I thought this was pretty cool, but they're talking about something a little different, and so this okay, so this is Clay's recursion tells that every total computable function which takes as a natural number as input and gives another natural number as output. There exists a particular input n such that two particular computable functions, phi sub n and phi sub fm, have the same input output characteristics. But I thought that this maybe is just an instance of the parameter theorem. By the parameter theorem, f of x computed by P of E, there exists an S, a one-to-one computable function such that P E of Z equals to P S of E of Z. So I think the code for the program that computes F will be this fixed point. That's what it seems like. But I mean, I'll go back and do this. Maybe we'll talk about this later, or just maybe you want to look at it. But I thought this was a really nice like blog entry. And then, oh yeah, I was talking about. And there's a cool picture. I didn't get a chance to like go through this though. But I think it's probably really cool. There's a lot of like the phi sub v program v calculating on itself or something. It looks really cool. And I was thinking about this little picture here is like when I have moments like right here, when I have moments when I understand this stuff and I feel like I really understand it, the feeling is like I feel like I'm in a graphic novel or a comic book and I'm like sitting having coffee with it's just like it's a really particular feeling about computability in particular, where it's like you feel like you're in a graphic novel. I don't know, it feels very like, I don't know what that's a good feeling. It feels like you're part of, like you're on the inside, but it's like flat or something. I don't know. And then when I'm not understanding it, I'm over here and I feel like I'm at the bottom of a cliff. I don't know how I got to that bottom of that cliff and there's rocks everywhere and I'm just sitting there all alone. And then when I understand it again, I'm like, oh, back in the graphic novel, having a coffee with whoever the character is. Okay. So what should we, I wanted to just mention, because I think I brought up at some point, just we talked about P versus NP, and I said these people, Stephen Cook, this is a good thing to read. Think I've probably tried to read it before. But that's a very nice statement, though. We can at least read that from all the ramblings I was doing last time. The P versus NP problem is to determine whether every language accepted by some non-deterministic algorithm in polynomial time is also accepted by some non-deterministic algorithm in polynomial time. And then Lena Levin was the other person, I think, that was like came up with this problem or something. Stephen Cook. Okay. And what else? Okay, so then let's read. Oh, then I have this paper here. Okay. Let me just do one thing, because I had this little like. Maybe we're over this stuff right now. Say my name. Okay, this was an interview with S. Okay, just because maybe to help us understand this parameter theorem. She's special. Okay, so hi, I'm S. What do you do? Suppose you have the X program and want to compute the Y slice. Ask me, and I'll tell you the code for your program. Okay, thanks, S. You seem like a real cool person. Okay, and it's one-to-one computable. Yeah, we saw that. Okay, so this is, I don't know if, okay, Claney is I believe that's how you pronounce the name, is Claney. I don't know if this is the paper that we're talking about. I believe it is, but it's all about like nerve nets, and I don't know. So I'm just going to read the first paragraph. I just thought it was like, there's something here you can read. I'm just going to read this page, and if it's something that is interesting, well, maybe we'll keep going, but maybe just for today. I just kind of like, what is going on here? Okay, so this is Claney. I say Claney. That's what I thought online. But if you know the pronunciation, please let me know in the comments. Okay, stimulus and response. An organism or robot receives certain stimuli via its sensory receptor organs and performs certain actions via effector organs. To say that certain actions are a response to a certain stimuli means, in the simplest case, that the actions are performed when those stimuli occur and not when they do not occur. Since both stimuli and the action may be very complicated, the relationship between the two is very complicated. In order to simplify our analysis, we may leave out of account the complexities of the response. To do this, we reason that any kind of stimulation, or briefly any event which affects action, in the sense that according as the event occurs or does not, under some set of circumstances held fixed, a different action ensues, must have a representation in the state of the organism or machine. Oh, even after the event has occurred and prior to the ensuing action. It's just so weird. It's like it has something to do with free will or something. Because I saw this like person discussing some interview, like like, what do we have free will, and like like someone's like shooting a gun, and like everything that led up to that, do they have a choice in that moment to stop? But it's also reminds me of Minority Report, but she says you do have a choice, you still have a choice. That's another good show. Okay, I'm going to go back to this post. I just want to read this. I do think we should just keep going, and I'll just read paragraph by paragraph. It's going to go slow, but I think like eventually, like, maybe it's, what are we on right now? Maybe we'll just get like, it's just absorbing or something. Also with post, I'm like, I kept thinking like, I can't understand what he's saying sometimes. And like when he says integral variable, that's something that's like, you say integral variable and my mind just like sweeps over, because it's like, I know those words, but I don't know what you're talking about. It bothers me. But it's like, okay, integer. But I guess now we don't say integral because then you might get confused with the integral. So it's integer. Okay, this is post. Okay. In the first example, the set is given by recursive enumeration thereof via the recursive function x squared. Okay, so in these examples up here. In the second example, the set is generated by a linear sequence, each new element being effectively obtained from the elements previously generated. In this case, by raising 2 to the power the sum of the preceding elements. The set is effectively numerable since the nth element of the sequence can be found, given n, regenerating the sequence through its first n elements. In the third example, we rather imagine the positive integers 1, 2, 3 generated in their natural order. And as each positive integer n is generated, a corresponding process set up which generates n squared, n cubed, n to the fourth. All these to be in the set. Actually, the standard method for proving that an enumerable set of enumerable sets is enumerable yields an effective enumeration of the set. They talk about a generated a lot. The other paper too, that other paper or something else was talking a lot about generating. Okay, let's read Turing. Oh, I had it. Okay, let me see if I can get it back. Enchendunk's problem. Enchendunk's problem. In a recent paper, Alonzo Church has introduced an idea of effective calculability, which is equivalent to my computability, but is very differently defined. Church also reaches similar conclusions about the Enthedunk's problem. The proof of equivalence between computability and effective calculability is outlined in an appendix to the present paper. We have said that the computable numbers are those whose decimals are calculable by finite means. This requires rather more explicit definition. No real attempt will be made to justify the definitions given until we reach section 9. For the present, I shall only say that the justification lies in the fact that the human memory is necessarily limited. Turing's paper is very readable. This is fun. Okay, we'll see what this next up is. Maybe it'll get really hard. Okay, cool. Okay, let's see here. All right. So I had a great time hanging out with you. And hope you got your freak on. And well, that's all for today. And so we'll see you next time on Computability Freaks.